Okay, so what we're going to do today is we're going to take a closer look at the amino acids as they're put into the polypeptide chain. And to do this, we're going to jump back and look at our biochemistry, in which we talked about amino acid structure. So we're going to talk about the N and the C end of the amino acid and what that means chemically. Then we're going to look at how, and just briefly, how the polypeptide chain folds itself up into an active protein. So that's our task now. First, amino acid structure. So all amino acids, every last one of them, have the same basic structure. And the way I like to think of this is they're all based around a single carbon atom. So at the heart of the amino acid is that biological atom that we love and we're made of, and that's carbon. So in the center, we have a carbon, and every carbon can make 4 bonds. So center.
We have notes on this.
So this is the way I remember it. You remember however you like. I remember that the amino acids are all centered on a carbon atom. And to that central carbon atom, we have 4 different things attached, because every carbon atom has 4 different things attached to it in a biological space. Okay? So there's 4 different spaces. One of them is easy. It's just a hydrogen. So on that central seat, we have a carbon. On opposite, there really is no opposite. On the other side I usually draw, we have an R group. And R isn't a particular element. R just stands for something else. And it can be very complicated, or it can be very, very simple. We'll call it an R group. And the R group is the key to the amino acid. Like, that's what makes all the amino acids different, is they all have different R groups. Yes?
Remainder group? Is that what the R stands for?
I don't know. I've never heard of remainder. Were we told this remainder?
Yeah.
Oh, a remainder it is. It's the key to the amino acid. Okay? It's the key. It's different for every amino acid. It's different for every amino acid, and not only that, it gives the amino acid its properties. The properties of the amino acid that are different are set by the R group. Okay? So whatever properties the amino acid has, it's the R group that has those properties. That's what the R group is for. It turns all the different amino acids into something different. Wonder how many R groups there are.
20.
Oh, there would be 20. Because, oh, you've got, excellent, you've got the sheet. So because there are 20 different amino acids, there must be 20 different R groups. Okay. In general. All right, so that's the R group. It's what makes each amino acid special. The remainder of the amino acids are the parts of the amino acids that exist for its linkage and its primary structure. And that is, we have an N part of the amino acid and a C part. And we're going to put the N part on the right just because. So there's, this is called the N terminal.
Mr. Blenman.
Or the NN, yes.
Oh, okay, you're putting it on the left?
Yeah, oh, sorry, I'm going to put it on the left. My mistake.
Yeah.
I think I said right, but I'm putting it on the left.
Yeah.
What is that at the bottom?
N terminal.
My left, you're right. Okay, here we go. This is the N terminal of the amino acid, and it's a.
C.
It is a.
It's
It's an amino group. It's a nitrogen base. So nitrogen can form 3 bonds. Yes, my friend.
Putting what it is. Oh, he's just showing like this entire section is the.
I don't understand your question. What 2 other bonding spots? Oh, these 2 spots. These 2 spots are for linking the amino acids together and helping it form its primary and secondary structure. That's what these two spots are for. They're linking the amino acids together and helping it form its primary and secondary structure. So this side here is what we call an amino group.
Amine group.
By group, we mean group of atoms. So amino group is simply a nitrogen and two hydrogens. In organic chemistry, this is called an amino group. And it means simply a group of atoms. And amine just means in with two hydrogens on it. Okay? You have to remember that while carbon can form 4 bonds, nitrogen can only form 3 bonds. And oxygen can only form 2 bonds. You got to keep that in your head. Those are your key molecules or your key atoms for amino acid structure. You also will eventually have to meet sulfur, because that's the other thing that's in amino acids, and it forms 2 bonds as well. And that's kind of important. But we'll itemize the bonds in a minute. All right, so this is called the N-terminal, and it's an amino group. The other side is called the C-terminal. Because it's another carbon group, and it's a carboxyl group. That's a carboxyl group.
Your nitrogen can form.
Sorry?
I was going to say if your nitrogen can form 3 bonds, then why would there only 2 hydrogens, but it's also bonded to the carbon.
Yeah, one of the bonds is going to be taking up, connecting it to the rest of the molecule. So we have an N-terminal and a C-terminal. The N-terminal is an amino group. The C-terminal is a carboxyl group. The dashes mean bonds, covalent bonds. Sometimes we summarize them. This should really, if I was really careful, I should do this. It's C bonded to an O, bonded to an H. But biologists often take shortcuts, chemists too, by just going OH. But by OH, we have to know it's O bonded to an H. It's kind of important. But we just shorten it to OH. We just do. This means the carbon has 2 bonds to the oxygen. Remember, every oxygen can have 2 bonds. We've got this carbon here that needs 4 bonds. So 1 bond takes it to the central carbon. 1 bond takes it to this OH combination. There's 2 bonds left, but rather than putting on 2 separate things, it's both going to the same thing, to the oxygen. So every dashed line here represents a bond, and a bond is simply a pair of shared electrons. We really don't need to know that. All we need to know is that this is a bond, a bond, a bond, and this is your basic structure for an amino acid. All amino acids have the same basic structure, every last one of them. If it has the structure, if it's an amino acid, if it's an amino acid, it has the structure. So, why is this called an amino acid? Well, it's called amino because one N is an amino group. It's called an acid because this carboxyl group is actually a carboxylic acid. I'm going to put that down here at the bottom. Can you see down here?
Yeah.
I can use the board right now, so it doesn't matter.
Okay.
I'm getting glasses soon, don't worry.
Alrighty. So this is a carboxylic acid group. That's another name for this carboxyl group. It's a carboxylic acid. And it's called acid because this little H here will take off and act like an acid. That's outside of this. So this is why we get the name amino acid. We get an amino group here and a carboxyl group there.
I don't see the difference.
Questions?
Carboxylic.
No.
Questions? All good? You've done this before?
Yeah.
Excellent. Okay, so now we're going to summarize the bonds really quickly that can be made. So number of bonds in biological systems. Carbon can make 4 bonds. Oxygen can make 2 bonds. Nitrogen will make 3 bonds. Hydrogen will only ever make 1 bond, and sulfur will only ever make, well, sulfur will make 2 bonds. Usually. It can behave quite differently. But for amino acids, we really want to consider sulfur just making 2 bonds. So this is number of bonds, and having this in your head can really help you dealing with these structures. So carbon will always make 4 bonds in biological molecules. Oxygen will make 2, nitrogen will make 3, hydrogen will make 1, sulfur 2, and bonds can double up. You can make 2 bonds between 2 things, and we saw that here, where oxygen can make 2 bonds, and carbon can make 4, and 2 of those bonds are going to the same thing. So carbon gets 2 bonds, one going to oxygen, and another one going to oxygen. And oxygen gets 2 bonds, one going to the carbon, and another one going to the carbon. So it's possible that things can double up. They can double up, and they can triple up, but no more. Okay? Not in any biological molecule. You will get double, and you will get triple, you get no more. It can be stable biological molecule. Okay?
You could do like 3 dashes.
Questions? Okay. All right, so you've got the chart? Good. All right, so what we're going to do now is we are going to look at how these amino acids come together to make our polypeptide. We're going to go 5' to 3' as if we were reading a messenger RNA. So our first amino acid comes in with the N terminal pointing in the 5' direction and the C terminal pointing in the 3' direction. So the sidedness and the directedness of the messenger RNA also specifies the sidedness and the directedness of the amino acid. So the messenger RNA is being read 5' to 3'. The amino acids come in N to the 5' end, C to the 3' end. So, the first amino acid, methionine, comes in N to the 5' end. So there's my central carbon, an amino group, the hydrogen, the carboxyl group. I'm going to break it up into O and H, you'll see why in the middle. And here's my R group. Okay?
That's the R group for methionine.
Well, yeah, what is the R group for methionine? Look it up on your chart. Okay? Now, the next one comes in with the N towards the 5' end and the C towards the 3' end. So we're going to put our next amino acid arriving. Here's our next amino acid arriving. Central carbon. One side has the amino group. There's a hydrogen. The other side has the carboxyl group. And of course, there's the R group, meaning telling us whatever amino acid this is. What is the R group for methionine? Yeah, it's in textbook, and apparently you were given a sheet.
Really?
Alrighty. Okay.
Booklets.
Alright. So, this now is the amino acid at the other side of the transfer RNA. Alright, it's a hydrocarbon chain involving a sulfur atom. So it's a 3-carbon chain with a sulfur atom on it. Okay? And yeah, it's done in organic notation, so that's why it's a little hard to read at this stage. We'll get easier in a minute. Alright, so this is the, we'll assume that this is our methionine, so this is a 3-carbon chain with a sulfur on it. This is the first amino acid that came in, so this would be in the P site. So it would be a transfer RNA at the P site, and at the other end of the transfer RNA is this molecule here. Actually, it's hooked up through here, but we'll just ignore that. It's hooked up through here. So we'll just look at them as if they were all by themselves. Okay? But in reality, it's hooked through here. All right, to the transfer RNA. The second one comes in the same direction. So this would be the one coming into the
A site.
the A site. This is the new arriving amino acid. And it will be hooked up through here. Right? It's actually a covalent bond right through here. But these two things, this one is free. This is hooked up through here. This is free. You're right, you get a dehydration synthesis. So you have an OH here and an H here. It doesn't matter which one. And when you have two H's and an O, you have a water. So this is another example of dehydration synthesis. Dehydrate, because you're removing water. So hydro is the word for water, and de means out. So this is a dehydration reaction. Okay. So the hydrogen from this attached to the nitrogen gets attracted to the oxygen that's already attached to one hydrogen to make water. So this hydrogen came from the amine group. This hydrogen was already attached to the oxygen, and you make water. Okay. What's the name of the enzyme that does this? Yes? Yeah, peptidyltransferase. It actually catalyzes this formation of the bond. Okay? So what do we get after this? We get this. You've still got the N-terminal, particularly for our first amino acid. That M-terminal is still sticking out there. We've got our central carbon. We have our R group. You've got that lonely hydrogen. It's attached through to the carboxyl group, but we took out the hydroxide, so the carbon ends up going right away to the nitrogen, still has the other hydrogen still attached, and then on to the rest of the molecule. The central carbon attached to the R group, attached to the R group, attached to the hydrogen, attached to the carboxyl group, and so on. Okay? So look here. This is the place where the two amino acids were joined together. And they were joined together by pulling away the OH that was here. I'm going to dot that in. The OH that was here and the H that was there, they got pulled away, and a new bond was formed. It's it's called an amide group, but we call this a peptide bond. And a peptide bond is simply the formation of this group. It's called an amide group. How do we have an amine group? This is an amide group. Okay, just a different one. But this is called this here
Peptide bond.
is called a peptide bond. This group here is an amide group. It's an amide group. That's what we've made by condensing a carboxyl group with an amine group. We make a new group that's called an amide group. So they could very well be called polyamides. We call them polypeptides because they're made by formation of a peptide bond. But they could have been given other names as well too, because every one of them is now going to contain this amide group between the two of them. All right. So what happened to the transfer RNA that was attached here? It went to the E site and gets flicked away, and this is now attached to here. This will be attached through here to the P site, and what will arrive? Another amino acid that will form a peptide bond here. Do you want me to do that for you? Show you? Yeah, you're okay. Wow, first time. You're like, so you get the idea. Another carbon. We're just gonna ghost it in here, just so we get the idea. Another amino acid will arrive.
Is that a ghosting? Because you're doing
Into the A site. This one will be attached to the P site. This one is floating, just attached by the peptide bond to the one that's attached to the transfer RNA in the P site. And then a new one will arrive at the A site, and peptidyltransferase will grab it and do a dehydration synthesis. So let's write that word down here because it's important for you to remember. Remember, this is a dehydration. One second. I can get these words right. So this is a dehydration synthesis D means from or out of. Hydro means water. So removing water and synthesis makes make. So you make something by pulling out of water. Question?
The transferase of the site won't have one of these.
The peptidyltransferase.
No, the transferase, the mRNA,
Yeah.
transfer RNA in the E site won't have any of these right? So it's cleaved off.
The transfer RNA in the E site, that's right. It's cleaved off, and this one is only attached now to the amino acid that's attached to the tRNA in the P site. That's right. In the P site is where the one that bond was just formed, and then the old ones are all there attached onto it. So if my hand is the transfer RNA, this is the one at the P site, this is the one at the E site, and all the previous ones are just there. Free. They're not attached to the ribosome anymore. And then the new incoming one,
They're all attached.
my hand is another transfer RNA. So my arm is a transfer RNA. This is an amino acid. So this is the P site.
Yeah.
Then the next one comes into the A site. Right? And then it makes the bond. And then this transfer RNA leaves, leaving the amino acid there attached at the P site as the chain gets longer and longer.
Yeah, let's see.
Okay? So, what do we notice about this? Well, we notice that the protein molecule so made is going to have an orientation. It's going to be made from the N terminal towards the C terminal. Okay? Yes?
Combining a carboxyl group and a amino group is creating
amide, A-M-I-D-E, amide group. Okay. All right. At the end of the protein synthesis, the last amino acid is released, and we have our polypeptide chain. Yes?
What happens to the water that is...
It's free into the cytoplasm. In fact, this formation of protein releases water. It just does. So there's a lot of reactions in your body that actually make water, produce some water. A lot of reactions in your body consume water as well too, it turns out. But it's a water generating reaction. So extra water is produced by this. It probably won't positively change the water balance because there's lots of other things that are happening in order for this to happen. For example, GTP has to be cleaved off. So you may in fact be consuming hydroxyl groups as you do that and losing water. Yes?
If we're producing water in ourselves, why do you think
As I was just saying, there's lots of other reactions in your body that consume water, right? Including removing digesting protein. So as new proteins are being made, old proteins are being digested. Obviously, the digestion of a protein will involve inserting the elements from the water into the protein, right? It's a reverse reaction. So that will consume water as well too. So, so you still have to drink water even though some reactions in your body make water. Other questions? All right, so what do we know? So protein is made, or the polypeptide is made from the N terminal towards the C terminal.
Isn't having a spare great? Isn't having a spare.
Alright, so polypeptide chains are produced from the N terminal towards the C terminal. What does that mean? That means that new amino acids are added to the C terminal of the existing polypeptide chain. All right, so the polypeptide chain exists with its C terminal there, and the new ones are always coming in at the C terminal with their incoming N terminal meeting the C terminal of the existing polypeptide chain. I know that you were told, I think, that the amino acid structure, that the primary structure was sort of just linear. We're going to give more details on that now. Amino acids really never exist as just a straight line. In fact, they can't, because none of these bonds are straight bonds. For the purposes of understanding and these structures, we draw them as if these bonds were in straight lines, but they are not. For just one quick example, the carbon atom has bonds which extend out towards the corners of a tetrahedron.
Whoa.
Okay? The 4 bonds are equally spaced. They have to be, because they're electrons. Electrons repel. So the 4 bonds are going to be equally spaced. Do you see how you cannot get a line now? Because every carbon is going to be a kink, right? It's going to be a bend. So the protein cannot exist in a straight line. It never does. The bonds are all at some angle. We don't get straight lines. Okay? So it is in a line, but the line is a zigzag line of the carbon backbone to the protein molecule. Right? Well, carbon-carbon, nitrogen, carbon-carbon, nitrogen. Backbone to the molecule, right? Carbon-carbon, nitrogen, carbon-carbon, nitrogen, right? Carbon-carbon, nitrogen, carbon-carbon. All right. The nitrogen bonds are like this.
But 3D.
They're flat. Because there's no other way to do it. Get your head around that for a while. Gio's like, but there'd be 3D. As soon as I moved it to a 3D, it's now closer than it would be like that. So this is as far apart as they can get. Yes, Ryan?
What enzyme catalyzes the hydrolysis of amino acids?
Maltase.
You were talking about that now in digestion. Hydrolysis of amino acids, you have trypsin, pepsin. You know, we've got all sorts of amino acids that are involved in the hydrolysis reaction. Right? So that's your digestion section that you're talking about. And what they do is they grab water and they push it in between the 2 amino acid residues, and so they separate. That's what they do. All right. So yeah, trypsin and pepsin, right? Your 2 main protein digesting enzymes. Sorry?
They ate them in the hydrolysis.
That's right. They reverse this reaction. They add a water molecule, separating the amino acids into shorter chains. All right. So we talked about how, for just as a background, I told you how the carbon atoms, the bonds are aimed towards the corners of a tetrahedron. So I think 109 degrees or so, right? And that's because they're equally spaced. So the next carbon is also sort of going to be kinked off into space. It's going to be a zigzag line as you trace the carbons along. Nitrogen forms 3 bonds, and the furthest way you can get them is 120 degrees. You can't get them any further apart than 120 degrees. Try it. As soon as you try to get 3D, these 2 are now closer. Okay? So this means that every nitrogen atom provides a kink in the chain as well too. So the chain cannot be straight. The chain always has to zigzag along. Okay? Not only that, these atoms have free rotation. So the constituents are allowed to rotate. You can picture this is coming into a bond, and this is a nitrogen atom. It can rotate. The bonds can all rotate. That's another reason why we don't see straight chains, is they're free to rotate. Absolutely free to rotate. Okay? All right. So, we're now going to talk about what happens to the polypeptide. As soon as the polypeptide is made, it begins to curl on itself. Okay? And that provides its secondary structure. All right, it's not the rotation, it curls into a stable structure. Let's talk about protein structure now, or polypeptide structure.
Some of their constituents like attract each other.
Exactly. That's the 3rd level. So first level, what we call our primary structure. Primary structure is our sequence of amino acids. Are you okay? Well, I've actually been doing it. I'm going to abbreviate amino acids as AA, save ourselves some time writing. So this means primary. Our primary structure is a sequence of amino acids. Methionine, valine, phenylalanine, isoleucine, methionine, whatever. Just amino acid after amino acid after amino acid. That's our primary structure. It can be as few as a dozen amino acids. It can be as many as 100 or more amino acids. Just one after the other. That's your primary structure. Amino acid after amino acid after amino acid after amino acid. Quick thinking question. Suppose my primary structure is that of insulin, which if I remember correctly is about 160 or so amino acids. So what length of messenger RNA is necessary to code for it?
360.
Yeah, exactly. Plus
Plus the starting, no, plus the end codon.
plus 3 for the end codon. Very good. Okay. So that's how it works.
Isn't it 120?
Wouldn't it be
No,
160
not
times 10?
translated.
Yeah, no, 120.
160. You said it's 160.
If I told you that my polypeptide was 169 amino acid residues long, what length of messenger RNA minimally could code for that? It would be that times 3 plus
The start.
plus 3. No, it might be included if methionine is there.
510.
Right? That's how it works. Now, does the primary structure of our polypeptide chain, this is polypeptides, but really we're talking about proteins, which are more than polypeptide chain. It's polypeptide plus everything else that's going to happen to this polypeptide chain. Our primary structure of the polypeptide chain is our sequence of amino acids. What amino acid follows, what amino acid follows, what amino acid. Here's a good point to tell you something. Every polypeptide chain does not begin with methionine, because in many of them, the methionine is clipped off before it makes an active protein.
Right.
So, because it doesn't want a methionine there. You'll know why in a minute, in a lesson. Yes?
So an amino acid always starts with methionine, but it doesn't necessarily always use methionine?
That's right. The first codon is methionine, and then it makes an amino acid chain with the methionine as the first. But for most proteins, that methionine is clipped off. Yes, with dehydration. It's right. Hydration. Hydrolysis. So, for many of them, that initial methionine is clipped off. It just got it started. The cell does not want a methionine on the end of its amino acid, and it's clipped off. It's part of the protein processing. Now, the first thing when we're talking about protein processing, until now we were talking about messenger RNA processing. Now the protein is processed. You see the themes emerging? How everything has got this processing step. It's not just made. Proteins are processed as well, and one of the first things that happens to many proteins is that initial methionine is clipped off, because the cell doesn't want an amino acid with a methionine on the end. And when we talk about the properties of methionine, you'll see why sometimes it's not good to have it at the end.
The cell needs to make a
Sorry?
The cell
needs to make it, well, it has to get the thing started. Just like, a primer is needed for something, it has to get it started, but once it's started, it needs to make only the, what it needs. Right? All right.
How can we stop waste on Earth if we are wasting each other's lives? You tell me. You tell me.
All right, now we're on to our secondary structure. And our secondary structure is created by hydrogen bonding in the polypeptide chain itself. And the secondary structure is two types. There are two possible secondary structures. Have we covered this? What are they?
Alpha, beta.
Alpha,
And beta.
helix, and a beta pleated sheet.
This is created by H, the hydrogen bond.
And this is created by hydrogen bonding Now I'm going to use the term backbone here to refer to that sequence of carbon-carbon nitrogen, carbon-carbon nitrogen, carbon-carbon nitrogen that extends throughout the whole polypeptide chain. Right? That part, not the R groups, but that part of the polypeptide that just continues through carbon-carbon nitrogen, carbon-carbon nitrogen, carbon, and it keeps on going on. There we get our hydrogen bonding. Now, for hydrogen bonding, we need two things. We need a hydrogen attached to an electronegative element, and we need an electronegative element somewhere else that's going to attract the hydrogen. Okay? So we need to understand this. Have you talked about hydrogen bonding much?
Yeah.
A little bit.
All right. So,
My mom bought
for hydrogen bonding to occur, we need two things. We need hydrogen attached and that's covalently. To now, for those of you non-chemists, this might be a bit much. Let me try to explain. Certain atoms really, really like to pull electrons into them. Okay? They don't like to leave electrons alone. They pull the electrons close. No, it's not oxidation. It's a covalent bond, but they don't share well. It's electron negativity. So in a covalent, exactly, in a covalent bond, electronegative elements So I'm going to use the word unfair, not because it's a good biological term, but because it helps us understand. These elements are hogs and bullies. They do not share well. They pull electrons towards them. So in electronegative elements, they unfairly share electrons. They pull the electron density towards them. So, electronegative element means that these are bully elements, nasty bullies. They're supposed to be sharing because they're in a covalent bond, a sharing bond. But they do not share. What do? They hog. They don't steal. They hog. Why do we say hog and not steal? Yes? That's right. If they stole it, they would take the electrons and the other guy would do without. Like a hydrogen ion, he'd do without electrons. But the other one, they get some electrons, but the electronegative element is hogging the lion's share, to use animal metaphors, of the electrons. Right? They're taking most of the electrons away. And that means that the other element, in this case hydrogen, has enough electrons or not quite enough?
Not enough.
Not quite enough because it's attached to a hog. Okay? Kind of like trying to share.
Imagine like a hog cherry. Like it's attached to a hog.
It's like trying to share fries with someone who doesn't share very well. Right? You get a fry, and for every fry you get, they take 3. Okay? That's like when hydrogen is attached to an electronegative element. Hydrogen tries to get the electrons, but it only gets a little bit of what it deserves because the other one is a hog. Okay? So,
Deep under.
for the hydrogen bond, first we need hydrogen attached or covalently to electronegative element. In a covalent bond, these electronegative elements unfairly share electrons. They pull electrons towards them. And who are these bullies? Who are these bullies?
The carbons.
No, not carbon. Carbon is really good at sharing.
It's really low.
Yes, and who are these bullies? No. Chlorine if it's there. But in this molecule, who's the bully?
Oxygen.
Nitrogen and
Nitrogen, oxygen.
Totally guessed.
so nitrogen and oxygen. Other bullies we might see are sulfur. And to a lesser extent phosphorus are bullies too. But right now it's nitrogen and oxygen that are these bullies. Okay? Now this is going to help us explain some stuff. Take a look.
This is Keith's instruction before the lunch bell. Would the following students please see Mrs. Allard in her office at lunchtime today? Janae Allen, Rafael Flores, Gilbert Kakosis, Ashman Boyle, Ellie Kazumba, Madeza Martin, Mojo Olanian, Guni Randawa, Yana Torino, and Brianne Wick. Those students should see Mrs. Allard in her office at lunchtime today. Thank you.
There's someone named Janae at our school.
Someone named Rafael Flores in the school.
Alright, so nitrogen and oxygen are bullies with respect to electron sharing. They do not share well. They hog electrons. And the poor hydrogen has to make do with too few electrons. This can help us explain how the protein formed in the first place. Remember this? This was the central carbon, and here's your carboxyl group.
It's a cube.
Right? And then on the other side is a nitrogen, and this is your second carbon, and this is your carboxyl over here.
It's my favorite. I love it.
Cube.
What can you tell me about this hydrogen?
First vegetable.
This hydrogen, what we just discussed. What about this hydrogen? It's
H2O dehydrated.
it
Turns it goes in water, doesn't it?
It's the one that's going to form water. But what do we know about the situation under which it has to live? It doesn't have, well, an atom doesn't have any control. Who's stealing its electrons? Nitrogen is stealing electrons from this hydrogen, right? Because nitrogen is one of our bullies. Now that hydrogen looks about, does it see anything close by that's probably absolutely full of electrons? No hydrogen. Carbons share. Look, here's an oxygen. Right? Here's some oxygen, and it's going to be full of electrons. So there's going to be an attraction from this hydrogen to this oxygen, because oxygen is a bully full of electrons. Meanwhile, the hydrogen's current partner is a hog. He looks over and he gets a little jealous. Look at all those electrons. I could be over there too enjoying some electrons. Right? Now, oxygen is going to make a choice. Carbon is sharing. Is hydrogen really good at sharing, or does it just get bullied all the time? It gets bullied all the time. So why share when you can bully? So it grabs the hydrogen and stop sharing.
Good life lesson.
Why share with bullies?
That's the basis.